In this video, we'll discuss definite integrals and the area under a curve. Let's look at the integral from x equal 3 to x equal 4 of the function x to the fifth integrated with respect to x. This is called a definite integral because we've got x values given on the integral, and what that means is that we're integrating the function over a specific interval just from x equal 3 to x equal 4. So the way we're going to calculate this is we'll find an antiderivative for x to the fifth, and I'm going to put that inside square brackets. So an antiderivative would be x to the 6 over 6, and we're going to record our limits of integration on the brackets. Notice that we didn't write plus c when we were calculating our antiderivative. We never need to write plus c when we're working with definite integrals. So if you've got an interval of x values given, meaning if you see numbers above and below that integral, then you do not need plus c in the calculation. Now, in terms of calculating this expression, what the numbers on these brackets mean is that we're going to calculate the value of the function at the top x value, that would be x equal 4, and then we're going to subtract off the value at the lower x value, meaning at x equal 3. So we'll be subbing x equal 4 into our function, figuring out what that value is, and then we'll be subtracting off the value of the function at x equal 3. So that will give us 4 to the 6 over 6 minus 3 to the 6 over 6. So our final answer then is going to be something over 6. We can grab our calculator to figure out the numerator. 4 to the 6 minus 3 to the 6 works out to 3,367. So there we have our final value. So notice that when you're calculating a definite integral, you're expecting to get a numerical answer at the end. One really useful application of definite integrals is finding the area under a curve. When we talk about the area under a curve, we're talking about the area bounded by some function y equals f of x, as well as the x-axis and a couple different x values, x equal a and x equal b. To calculate the area under the curve, we're going to be calculating the definite integral from x equal a to x equal b of whatever function we're working with, and that will be integrated with respect to x. So that is a formula for calculating area under a curve. For our first main example, let's calculate the area under the function y equals root x plus 3 from x equal 4 to x equal 9. Well, the area is going to be defined as the integral from 4 to 9 of the function root x plus 3, and we'll be integrating with respect to x. So first thing we might like to do here, just rewrite that root x as x to the 1/2. That could be a mental step if you like. Next, we will calculate the antiderivative or an antiderivative for that particular function. So the power on the x is going to increase. We'll have x to the 3/2 times the reciprocal of that new exponent, and then an antiderivative for 3 is going to be 3x. Remember that we don't need plus c because this is a definite integral. What we do need is the limits of integration on the brackets there. Now to evaluate this, we're first going to sub our top x value, x equal 9, throughout this expression. So we'll have 2/3 times 9 to the 3/2 plus 3 times 9. And typically I write a set of square brackets there just to make it a little bit easier to follow along. And now we need to subtract off the value of that function at x equal 4. So we'd have 2/3 times 4 to the 3/2 plus 3 times 4. It's very important to have brackets on the second part of the expression because we do need to make sure that both of these terms are subtracted off. Now let's do some algebra. We've got 2/3 times 9 to the 3/2 is going to be 27 and we're adding 27 to that. And then I'm going to be careful about the signs here. We're going to have minus 2/3 times 4 to the 3/2 is going to give us 8. And we're going to have minus 12. So let's be super careful about the signs in this part because we had that negative sign applied to both those terms. The last two terms here are going to be negative. Let's continue to simplify. I'm going to write this as 54/3 minus 16/3. So I'm just grouping the two fractions together at the beginning of the expression, and then grouping these two guys together. Let's group these two guys together. We'll have plus 15. So that's looking like 38/3 plus 15. And let's think of that 15 as 45/3. So adding those together, we get 83/3. So that is our final answer in exact form. The area under the function y equals root x plus 3 from x equal 4 to x equal 9 is going to be 83/3. Second major example, let's evaluate the definite integral from x equal 2 to x equal 3 of this function with respect to x. Now this integral is too tricky to evaluate directly, so let's do a little substitution. Let's let u represent x cubed minus 3x squared plus 6. That would be a good substitution to make because then this expression here becomes much simpler. We can just call that u to the 4th. Now remember that if you're subbing u into an integral, you need to also figure out what du is equal to. Du is defined as the derivative of this expression times the differential. So the derivative would be 3x squared minus 6x, and that all has to be multiplied by dx. Now in this case it's probably a little bit better to think of du as being 3 times x squared minus 2x with respect to x, and we'll see why we need to factor it in a moment. The idea is that if we look back up at the integral, we need to rewrite the rest of the expression. So we've got this x squared minus 2x that needs to be rewritten. We've also got the dx that needs to be rewritten. These guys are being multiplied together. So let's see if we can figure out what x squared minus 2x times dx is equal to. And we need to rewrite it using the value of du. So looking up at this line here, if we were to divide both sides of that expression by 3, we'd have x squared minus 2x times dx is equal to du over 3. So that's going to be the secret to rewriting this integral. We're thinking of this product here, this expression times that guy, multiplying them together, we're creating du over 3. So now, with all that work done, let's rewrite our integral. The original integral in the question is the integral from x equal 2 to x equal 3 of an expression that looks like u to the 4th du over 3. Notice that these original values, 2 and 3, they were x values, so we do really need to say x equal 2 and x equal 3. We'll see why that's important later on. So at this point, let's focus on our integration. If we integrate u to the 4th, we're going to get u to the 5 over 5, and that's being multiplied by 1/3. So let's write it like that. Because it's a definite integral, we don't need our plus c, but we do need to record our limits of integration. So we've got x equal 3 at the top and x equal 2 at the bottom. All right, so we're looking at u to the 5th over 15. We'll be evaluating at x equal 3 and then at x equal 2. And in order to actually sub in these x values, we're going to have to write this back in terms of x. So let's remember that u was x cubed minus 3x squared plus 6. So we've got that whole expression raised to the 5th power divided by 15, and we're going to be evaluating at x equal 3 and x equal 2. So let's now sub in. Subbing x equal 3 into this numerator here, you can check that you're getting 6 to the 5th, and that's over 15. And then we're supposed to subtract off the value that we get when we sub in x equal 2. So I'm going to put square brackets here just to make this easier to read. Subbing in x equal 2, you can check that in the numerator here, you're going to get 2 to the 5th, and then that's over 15. So overall, we've got something over 15, and if we grab our calculator, we can check that the numerator comes out to 77.44. So the value of that integral, 77.44 over 15. Now I want to show you an alternative way of handling these limits of integration when you're making a substitution into a definite integral. Another way of dealing with this would have been to say, well, we were originally starting with x equal 2 and x equal 3, and let's see if we can just turn these into u values so that we can write everything in terms of u. So we need to look back at our original substitution that we made. Remember that u was this cubic polynomial here, was x cubed minus 3x squared plus 6. And let's try plugging the x value 2 into this expression here. So we'll figure out what u value that corresponds to. So that would give us 2. An x value of 2 plugged in here gives us a u value of 2. If we do the same thing for x equal 3, plugging back into this expression here, we're going to get a u value of 6. So another way to deal with the substitution would be to say the original integral in the question is going to be the integral from u equal 2 to u equals 6 of u to the 4th du over 3. So now these numbers here, these 2 and the 6, they're u values, so we don't need to write u equals 2 or u equals 6. The variable u is already implied by how the function's being written. All right, so now we can do our integration. An antiderivative is going to be u to the 5th, and that's going to be over 15. We don't need a plus c because it is a definite integral. What we do need is the limits of integration. So here you could write u equal 2, u equals 6, but again it's implied that these are u values because our function is written in terms of u. So now it's a lot easier to sub in. We're going to directly sub in the u value 6 here. That's going to give us 6 to the 5th over 15. And then we're going to subtract off the value that we get when we sub in u equal 2. So that will be 2 to the 5th over 15. So our final answer then will be something over 15, and if we grab our calculator we can check it's 77.44 over 15. So this gives us the same answer as the first approach. Both approaches are valid. The idea is that here we spent a little bit more time writing the limits in terms of u, but because we invested some time there, we got a nice payoff at the end of the question. The calculation went a little bit more quickly at the end. So both approaches are valid. It's just really a preference whether you choose to rewrite your limits of integration or whether you choose to leave them in terms of the original variable.